Folks, welcome to Statistics. What's up, folks? Welcome to the next lecture of Statistics. Welcome back to the next lecture in Statistics. Today we're going to be taking a look at how to solve problems involving binomial, geometric, and normal probability models. Alright, so let's take a look at our example, shall we? So we have the following. 20 donors at a blood drive. 6% are universal donors. Now what does that mean? Universal is a magic word. It means that your blood can be given to anyone and it will be accepted. Okay, so it's a kind of a Goldilocks zone, a kind of a magical type of blood. Okay, so that being said, we want to find the mean and standard deviation of the number of universal donors. All right, okay, so how do we get started with that? Well, first, to answer these questions, you're going to see what you're given. What I'm given here is the number of donors at the actual blood drive and the percentage of them that are universal donors. So that tells me two key things. Number one, it tells me the number of people I'm concerned with. So that can be thought of as my sample size, if you will. So that's going to be 20 donors, or it can be thought of as the number of trials. Okay, 6% are universal donors. That means my proportion of success is going to be 0.06, or sometimes we like to put the 0 out in front. So instead of 0.06, let's write 0.06. Okay, so now with that being said, how can we find the mean and standard deviation of the number of universal donors? Well, the first thing we have to do is think about the types of distributions we can use. We can think about geometric or binomial. Those are our two options right now. Geometric model or a binomial model. And each of them answers a different type of question. So we need to see what question we're interested in answering and then choose the type of model. So let's see, we want to find out the mean and standard deviation of the number of universal donors, and what is the probability there are 2 or 3 universal donors in 20 donors. Well, geometric models are really for answering questions that are in the form of how many trials until one success, whereas a binomial model is more for how many success, or what's the probability that there's going to be 5 successes in 10 trials. And that sounds a lot like what we have here. What's the probability there's 2 or 3 universal donors in 20 trials or 20 donors? So that calls for a binomial model. Okay, so now that we know what type of model to use, let's check out some of the formulas that we have to use for the binomial model. So for the binomial model, these are the formulas we're interested in using. The binomial model tells us the following. It tells us that the mean, or the expected value of a random of a trial, can be given by n times p, where n is the number of trials, p is the proportion of success. Okay, now with that being said, what is my n? It's 20. What is my p? It's 0.06. And so my expected value should be 20 times 0.06. Okay, now to find out what that is, I'm going to go ahead, go to the calculator app right here, and we're going to calculate what our expected value is. It should be 20 times 0.06. So let's see what that gives us. It's 1.2, and so our expected value is 1.2. That's our expected value right there. So hopefully that makes sense how I got that. Okay, now given that expected value, now we can find the standard deviation. Not too hard. The standard deviation for a binomial probability model is given by NP, just like expected value. But now you have to introduce the complement of P, which is Q, the proportionality of failure, and take the square root of all of this. And so I already know what NP is. It comes straight from the expected value. It's 1.2. What's my Q? Well, Q is the complement of P, right? So it's going to be 1 minus whatever P is. And since P is 0.06, I think that Q should be 0.094, or rather 0.94. Okay, so now with that being said, we can go back to our calculator and plug this in. Let's see what we get. 1.2 times 0.94, and that gives us 1.128. And so with that answer, we can go ahead and plug that right in. This is equal to the square root of 1.128. And how can we find out what that is? Well, go back to your calculator, folks, and let's see what the square root of 1.128 is. So come over here and put the square root symbol. And now I can find out that the square root of this is 1.06, which is as expected. If you have the square root of 1, it's going to be pretty close to 1. So this is about 1.06. So that's our standard deviation. Okay, that's our standard deviation of our variable. And so now what can we do? Well, check out all the work we've done so far. We've already answered the first question, which is the which is the mean and standard deviation of the donors. And what is our mean? Well, let's kind of try to highlight that. Our mean is as follows. Our mean is 1.2. And what is our standard deviation? Our standard deviation is a little more than 1.06. Okay, so we have our mean and standard deviation. Now, before I continue on, I'd like to address the fact that to even use the binomial or geometric models, you need to be conducting Bernoulli trials. So let's talk about that for a bit. Bernoulli trials. Now, Bernoulli trials have 3 major conditions. Okay, and the third one I'd say is arguably the hardest. Bernoulli trials have the following conditions. Number 1, for your experiment or study or whatever to be considered a binomial trial, you need to have the following. Number 1, your probability of there needs to be only 2 outcomes: success, which can be denoted with P, okay, that's our success, or failure, okay, that is denoted as Q. And since we're talking about probability, Q is of course just going to be 1 minus P. Another way you can think of it is that P and Q always have to sum up to 1. Okay, so that's the first rule of a binomial trial. Number 2, we need to always hold P constant. The proportion of success, P, must be constant. It must always be constant. Okay, that's the second rule of a Bernoulli trial. And the last rule of a Bernoulli trial is the fact that you must have less than 10% of your population. Okay, you must be dealing with less than 10% of your population so that all of your trials are independent. Okay, otherwise, and that's only if you're doing it without replacement, by the way. If you're doing it with replacement, you don't have to really worry about that. Another way we can say it is less than 10% of the population needs to be tested or part of your experiment in order for your trials to be independent. Okay, so does our problem match up with those conditions, with those restrictions? Well, yes, it does, because the probability of success, which is what? The probability of success always remains constant. Do you see that? 0.6% is always constant, right? It never changes, right? Our probability of success always is constant. And of course, there's only 2 possibilities. You can either succeed in finding a universal donor or fail. Okay, and so those are the possibilities. And so because of that, and because we're testing much less than 10% of our population, this meets the criteria for a binomial trial. And so thus we found what our expected value is. That's a mean. We found our standard deviation. Here it is, 1.06. And you might be asking 1.2 what? 1.2 universal donors. 1.06 what? 1.06 universal donors. Okay, so don't forget your units. And let's take a look. Let's see if we can do our final question. What's the probability there are 2 or 3 universal donors? Well, to find probability in Bernoulli trials, with binomial trials models, we use a special formula. Okay, and let me introduce you to the formula. First of all, here's the formula. And it looks pretty crazy, but let's work through it. Okay, so what do we have here? We have the following. We have a bunch of things going on here. This right here, P you recognize as the probability of success, right? Hopefully you see that. P is just your probability of success. You're going to succeed how many times? Well, this right here tells you, I want to succeed K times. That's why we raise the proportion of success to the kth power. And I have a total of n trials. If you succeed k times, but you have n trials, that means you fail n minus k times. And so that's why we raise the failure proportionality to n minus k. And so this bajango over here, this yellow factor right here, what that tells us is the number of ways we can succeed and fail. Okay, so that's the formula, and now we can use it to find the probability that we have either 2 universal zoners or 3 universal zoners. So let's go ahead, go all the way back, and let's see if we can use this formula to our advantage. So let's go ahead and write all of this down. What can we write down? Well, we want to find the probability that we either get 2 or 3 universal zoners. So probability that x equals 2 plus probability that x equals 3. Well, what's the probability x equals 2? Well, we have 20 people in line. We want 2 of them to be universal zoners. So we raise the proportion of success constant to the second power, because we're going to succeed 2 times. And we're going to raise the failure proportionality to the 18th power, because we're going to fail 18 times. And that's that. And of course, we're going to add this to what? Well, let me go ahead and copy all of this. Let's see if I can copy this. That would be pretty amazing. Copy. And let's see if I can paste that right there. Oh, almost. We almost got it in. Okay, so that right there is the second part of my computation. That's the part where I want to find the likelihood of finding 3 universal zoners, not just 2. And so instead of 2 over here and 2 over here, I'm going to replace it with finding 3 successes and 3 universal zoners, and failing thus not 18 times but 17 times. And go ahead and calculate that. Let's see what that's going to be. If I bring out my calculator, we can go ahead and plug and chug this in and see what we get. So let's delete all of this. Okay, so this is going to be a huge computation, but I think we can do it. We're going to have 20 choose 2, which I don't think is available in this calculator. Unfortunate. So we're going to have to do it the traditional way, for at least for the combinatorics. So 20 choose 2 is what? It's 20 factorial over 18 factorial over 2 factorial. 0.06 squared, 0.94 to the 18th. Okay, likewise, let's perform same computation here. 20 factorial over 17 factorial over for 3 factorial times 0.06 to the third power times 0.94 to the 17th. And so, can we figure this out? Well, what's that going to be? It's going to be 20 times 19 over 2 times 0.06 squared times 0.94 to the 18th. Likewise, over here, I'm going to have 20 times 19 times 18 over, well, 3 factorial is 6, we know that. And this is going to be multiplied by 0.06 to the third and 0.94 to the 17th. Okay, we're almost there, ladies and gentlemen. So this right here goes into 20 10 times, so I'm left with 190 times 0.06 squared times 0.94 to the 18th plus what? Well, 6 goes into 18 3 times. 3 times 20 is 60 times 19 times 0.06 to the third times 0.94 to the 17. And now let's put this monster of a computation right in the calculator. Okay, so 190, that's gonna give you right here 0.3101, and so our final answer is gonna be 0.31057. And so
Embedded plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO, and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today And the first 50 of you to use that link will get a 20% discount on the brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.